Welcome, my friends. In this video, we will use the trigonometric identities that we already know to prove new trigonometric identities. Let's first review the trigonometric identities that we already know. Here are the reciprocal identities, which allow us to convert from each trigonometric function to its corresponding reciprocal function. Here are the quotient identities, which allow us to convert from tangent or cotangent to sines and cosines. Here are the three Pythagorean identities. We have sine squared plus cosine squared is equal to 1, 1 plus cotangent squared is equal to cosecant squared, and 1 plus tangent squared is equal to secant squared. I also have common algebraic manipulations of each of these three Pythagorean identities, solved for sine squared, cosine squared, cotangent squared, and tangent squared. Finally, we have the even and odd identities, which help us deal with negative angles. Cosine and secant are the only two even trigonometric identities, and sine, cosecant, tangent, and cotangent are odd. Let's take a look at our first problem. We are asked to prove the identity 1 minus cotangent of x all squared is equal to cosecant squared of x minus 2 times cotangent of x. The idea with proving an identity is to choose one side to work with and then manipulate that side either using algebra or trigonometric identities until it matches the other side. What you should not do is work on both sides simultaneously. You should pick one side to manipulate until it reaches the other side. We will complete our proof in two columns. The first column will be titled Statement, which is where we will manipulate one side of the equation. The other side will be titled Rule, where we will justify each manipulation that we make in the statement column with either algebra or some trigonometric identity. The first step will be to choose one side of the equation to work with. Typically, you want to choose the side of the equation that you think you have an identity for, or that can be easily simplified using algebra. Generally, if one of the sides looks nastier, that's typically the side you will want to work with. I'm going to choose to work with 1 minus cotangent of x all squared in this case. We can multiply this out so that we get 1 plus cotangent squared minus 2 times cotangent of x. This is due to the common algebra rule of a plus b squared is equal to a squared plus b squared plus 2ab. A is 1, so a squared is 1. B is negative cotangent of x, which when squared gives us cotangent squared of x. A times b is 1 times negative cotangent of x, which is negative 2 times cotangent of x when we add the 2. Next, you should hopefully recognize that 1 plus cotangent squared of x is a Pythagorean identity. Specifically, this is equal to cosecant squared of x. So our next step will be to substitute cosecant squared of x in for 1 plus cotangent squared of x. The result will be cosecant squared of x minus 2 times cotangent of x. At this point, we have completed our proof. We have manipulated the left-hand side of the equation so that it matches the right-hand side, so we are finished. Let's try another problem. We are asked to prove the identity 1 minus sine x times 1 plus sine x is equal to cosine squared of x. I recognize the left-hand side of the equation as multiplication by the conjugate. We have two expressions which are exactly the same, with the only difference being the sign in the middle, either minus or plus. If that's the case, when we FOIL those expressions, the two middle terms will cancel. Let's work with the left-hand side. If we FOIL this out, when we multiply the first terms, we will have 1 times 1, which is 1. When we multiply the outer terms, we will have 1 times sine of x, which is sine of x. The inner terms, we will get negative sine of x times 1, which is negative sine of x. And then the last terms, we have negative sine of x times positive sine of x, which gives us negative sine squared of x. We notice that the two middle terms cancel, which we knew was going to happen because we were multiplying by conjugates. This leaves us with 1 minus sine squared of x. We justify this step by algebra, more specifically FOIL. At this point, we have a squared trig function. Anytime you have a squared trig function, you can use a Pythagorean identity. One of the three Pythagorean identities is that sine squared plus cosine squared is equal to 1. If we subtract cosine squared to the other side of the equation, we will get that sine squared is equal to 1 minus cosine squared. We can substitute 1 minus cosine squared in for sine squared. Let's see what we get. We have 1 minus, parentheses, 1 minus cosine squared. Make sure that you use parentheses, because we must subtract the entire expression 1 minus cosine squared. we can distribute the negative sign so that we get 1 minus 1 plus cosine squared. The 1's will cancel, and we will be left with cosine squared. We justify this final step by algebra, distribution, and simplification. At this point, we are finished with the proof. We have manipulated the left-hand side of the equation so that it matches the right-hand side. Let's try another problem. We are asked to prove the identity secant to the fourth power of x minus secant squared of x is equal to tangent squared of x plus tangent to the fourth power of x. Let's work on the left-hand side of the equation. We know in general if we had x to the fourth power minus x squared, this could be factored as x squared times x squared minus 1. X squared times x squared is x to the fourth power, and x squared times negative 1 is equal to negative x squared. This can be applied to the expression that we have. We have something to the fourth power minus something squared. So this can be factored as secant squared times secant squared minus 1. Next, we notice that we have two squared trig functions. Squared trig functions relate to Pythagorean identities. The Pythagorean identity related to secant is 1 plus tangent squared is equal to secant squared. So therefore, each time that we see secant squared, we can replace that with 1 plus tangent squared. We get 1 plus tangent squared times 1 plus tangent squared minus 1. In the second expression, the positive 1 and the negative 1 cancel. We are left with 1 plus tangent squared times tangent squared. Let's distribute. 1 times tangent squared is tangent squared, and tangent squared times tangent squared is tangent to the fourth power, because we can add the exponents. We justify this final step by algebra, simplification, and distribution. At this point, we have finished the proof. We have manipulated the left-hand side of the equation so that it matches the right-hand side. How about this one? We have 1 minus cosine squared times cotangent is equal to sine times cosine. Well, we only have one squared trig function, so perhaps that's where we should start. Let's work with the left-hand side. We have 1 minus cosine squared times cotangent. We know that sine squared plus cosine squared is equal to 1. If we subtract cosine squared to the other side, we get that sine squared is equal to 1 minus cosine squared. We have 1 minus cosine squared in our problem, so we can replace that with sine squared. Altogether, we have sine squared times cotangent. Now, it's generally a good idea when you have trig functions that are multiplied or divided together to turn everything into sines and cosines to see if something will cancel. We know that cotangent can be written as cosine over sine by the quotient identity. So we can rewrite this as sine squared times cosine over sine. We have sine to the second power divided by sine to the first power. One of these signs will cancel. We will be left with sine times cosine, which is exactly what we wanted. We justify this final step with algebra, simplification. At this point, we have finished our proof. Let's see if we can prove sine squared times 1 plus cotangent squared is equal to 1. Let's work with the left-hand side. Now, we could either change sine squared, or we could change 1 plus cotangent squared. They both have Pythagorean identities related to them. I always remember that 1 plus a tangent squared related function is a Pythagorean identity. And in this case, we have 1 plus cotangent squared, which is equal to cosecant squared. Therefore, we can replace 1 plus cotangent squared with cosecant squared in our problem. From here, we have multiplied trig functions. Typically, when you have trig functions that are either multiplied or divided, you should change everything to sines and cosines, and typically something will cancel. We know that cosecant is the same thing as 1 over sine by the reciprocal identity. That means that cosecant squared will be the same as 1 over sine squared. These sine squares will cancel, and we will be left with 1 by algebra simplification. At this point, we have finished our proof. Let's see if we can prove that 1 plus tangent squared times cotangent squared is equal to cosecant squared. Let's start with the left-hand side. Again, we have 1 plus a tangent squared related function. I always remember that 1 plus tangent squared, or 1 plus cotangent squared, is a trigonometric identity. Specifically here, 1 plus tangent squared is equal to secant squared. Therefore, we can replace 1 plus tangent squared with secant squared in our problem. We have secant squared times cotangent squared. Like I've been stating, when you have trig functions that are multiplied together, change everything to sines and cosines, and typically that will simplify things. Secant is the same thing as 1 over cosine, and cotangent is the same thing as cosine over sine. We justify this by the reciprocal identity for secant and the quotient identity for cotangent. At this point, the cotangents will cancel, and we have 1 over sine squared. We justify this by algebra simplification. 1 over sine squared is the same thing as cosecant squared, by the reciprocal identity. At this point, we are finished with the proof. We have manipulated the left-hand side of the equation so that it matches the right-hand side. Let's try one final problem. We are asked to prove the identity 1 minus cosine times 1 plus cosine is equal to 1 over 1 plus cotangent squared. Again, I am recognizing that the left-hand side is multiplication of the conjugate. We have two terms which are exactly the same except for the sign in the middle as plus or minus. In that case, we know that when we FOIL out this result, we will get two terms that will cancel each other. So we will just have 1 minus cosine squared. The two middle terms would be 1 times cosine, which is cosine, and then 1 times negative cosine, which would be negative cosine. Those two terms would cancel, and we would just be left with 1 minus cosine squared. We justify this with algebra. We have the common rule that a minus b times a plus b is equal to a squared minus b squared. Next, we notice that we have a squared trig function. Anytime you have a squared trig function, you can use a Pythagorean identity. I always remember that 1 minus cosine squared is equal to sine squared, or that 1 minus sine squared is equal to cosine squared. If you take 1 minus either sine squared or cosine squared, you always get the other one. So in this case, 1 minus cosine squared is the same thing as sine squared. And this is by the Pythagorean identity, specifically the algebraically manipulated form. At this point, it might be unclear what we should do next. We know that our goal is to get 1 over 1 plus cotangent squared. If you glance at your identity list, you might notice that 1 plus cotangent squared is the same thing as cosecant squared. We basically have a cosecant squared in the denominator because sine squared is the same thing as 1 over cosecant squared by the reciprocal identity. At this point, we can use the Pythagorean identity for cosecant squared to convert this to 1 plus cotangent squared. At this point, we have completed our proof. We have shown that the left-hand side is equal to the right-hand side. Alright my friends, that finishes this video of practicing proving trigonometric identities.